in this video, we'll be focusing on solving paper 2 problem of IB physics, topic 2 mechanics. So this problem has two parts. Part A is about Newton's law of motion and kinematics. So it says car I and B are on a straight racetrack. I is moving at a constant speed of 45 meters per second, and B is initially at rest. B started to move with a acceleration of 3.2 meters per second squared. So let me just label all of those things. At a later time, B passes I. You may assume that both cars are point particles. A third car O with mass of 930 grams, a kilogram joined the race. O collide with I from behind, moving along the same straight line as I. Before the collision, the speed of I is 45 meters per second, and its mass is 850 kilograms. After the collision, I and O stick together and move in a straight line with an initial combined speed of 42 meters per second. So this is the mass of car I. This is a speed. So let's take a look at the problem. Show that the time taken for B passes I is approximately 28 meters per second. Oh, by the way, you can also find the problem in this link. It is an online version of Questionbank. So we know when I passes B, B starts to move with a constant acceleration of 3.2 meters per second. So in order for B to passes A, the two cars must travel a same displacement, right? Because we know B is here and I is here. So when B finally passes I, they gotta travel a same displacement. Right. So B moves with a acceleration of 1.6, so and has an initial speed of 0 meters per second, right? So by using the formula, you can actually find the displacement of B. So this is the displacement traveled by car B, and for I, because it has a constant speed of 45, so the displacement is just gonna be equal to 45t. Now you can solve the equation here. So 1.6t squared is equal to 45t. So 1.6t is gonna be equal to 45, and t is approximately equal to 28 seconds. For this problem, you just need to realize that the displacement traveled by B and I are equal, because when B passes car I is here and B is also here. And then if they chase each other, they gotta travel at the same displacement. Calculate the distance traveled by B in this time. So you already know how to calculate. Just use this equation here. So let me rewrite everything. So xb is gonna be equal to a half times acceleration times t squared, which is equal to a half times 1.6 times 28 squared. So this is equal to 1300. with a unit of meter. B slows down while I remain at a constant speed. The driver in each car wears a seatbelt. Using Newton's law of motion, explain the difference in the tension in the seatbelt of two cars. So Newton's law states that when an object is moving at a constant speed or is stationary, the net force of the system must be equal to 0. So B is slowing down, so there's gotta be a force, right? Since net force is equal to mass times acceleration. So because there's a force, there's gotta be a force in the seatbelt for car B, right? But for car I, because car I is moving at a constant speed, the net force of the system is 0 Newton. So there's no tension force in the seatbelt. And this is the difference between those two cars. The next question asks you to calculate the speed of O immediately before the collision. So car O has a mass of 930 kilograms and it collides with car I from behind. Before the collision, car I has a velocity of 42 meters per second and a mass of 850 kilograms. After the collision, they stick together. So this is an elastic collision and moving at a speed of 52 meters per second. So now you're asked to find the initial speed of car O. So we can use conservation of momentum to do this problem. So let me do this here. So by using conservation of momentum, we know that initial momentum must be equal to final momentum. So the mass of car O times its initial velocity plus momentum of car I is gonna be equal to the sum of their mass times their combined velocity. And we know all of those quantities, right? So O has a mass of 930 kilograms, and we don't know its initial velocity. And car I has a mass of 850 and a constant speed of 52. So this is going to be equal to 930 plus 850 times their combined speed, which is 52. So by solving this equation, we know the initial velocity of car O is going to be equal to 58 meters per second. So when you are doing the problem, make sure you label everything, right? So you know how to do the problem. So the speed is 58 meters per second. The duration of collision is 0.45 meters. Determine the average force on O. Well, from the last part of the question here, we know it's change in momentum. We know its initial velocity. And we also know its final velocity. And we also know the mass. So we can know the change in momentum. And change in momentum is equal to average force times delta T. And we know delta T. So we can solve the average force by using change in momentum is equal to impulse. So this is the initial velocity of car O, and final velocity is equal to 52. And the mass of car O is equal to 930 kilograms. So change in momentum is equal to force times delta T. And change in momentum is equal to mass of car O times final velocity minus initial velocity, which is equal to 930 kilograms times 52 minus 58. And because we want to find the force, we know that delta P, so change in momentum over change in time, is going to be equal to force. And the time given by the question is 0.45 seconds. Right. Now determine the average force. So since it's asking us to find the average force, I'm gonna take the magnitude of this quantity. So I'm gonna put an absolute sign here. And this will give you an answer of this number here. So this is the average force. From D to G is about electricity and magnesium. The circuit shown is used to investigate how the power developed by a cell varies when the load resistance R changes. The variable resistor is adjusted and a series of current and voltage reading are taken. The graph shows the variation with R of the power dissipated in the cell and the power dissipated in the variable resistor. So an ammeter and voltmeter are used to investigate the characteristic of a variable resistor R. Say how the resistance of an ammeter and voltmeter compared to R, so the reading of the instrument are reliable. So for ammeter, it gotta has a resistance of 0, because we want to measure current in the circuit by using an ammeter. So we don't want the instrument itself to have some resistance. So because if it has some resistance, the total resistance of the circuit changes. So the current of the circuit will also change. And so for voltmeter, it's gonna have an infinite resistance, so that no current will be going through from here to here. Right? So no current will be going through the voltmeter. Show that the current in the circuit is approximately 0.7 ampere when resistance is equal to 0.8 ohms. So there's a graph that shows you the power. So you know the power and you know the resistance. How do we find current? So power is equal to voltage times current, which is equal to current times resistance times current. So it's going to be equal to current squared times resistance. So current is going to be equal to the square root of power over resistance. Oops. So we know the resistance is equal to 0.8 ohms, and we want to find the power dissipated by the resistor. So this graph here. So let me zoom in this image. I hope this is clear enough. So 0.5, 0.6, 0.7, 0.8, 0.9, 0.8 is here. Alright, seems like this line. So here is 1, 2, 3, 4, 5. So here is gonna be 0.24, 0.28, 0.28. Here is gonna be 0.36. Right. So here is gonna be 0.36 watts. So the power is 0.36, and then you can plug in a number. And it's gonna give you a number of 0.7 ampere. Alright. The next problem asks you to find internal resistance of the circuit. So we know if there's some internal resistance, then the power of the variable resistor is not gonna be equal to the power dissipated in the cell. So the difference in power is due to internal resistance. So when the resistance of the variable resistor is equal to 0.8 ohms, the current is equal to 0.7 ampere. And we also know the power dissipated by the cell as shown in the graph. So you can calculate the resistance, internal resistance. So here. So it seems like it's in the middle. So this is going to be equal to 0.58 watt, right? So the power is equal to 0.858 watt. So now you can calculate the internal resistance. P cell is gonna be equal to current square times the internal resistance. So I'm gonna represent that by using AR. So this is because theoretically the power by the variable resistor should be the power of the circuit, right? Because the battery terminal, they're supposed to have zero internal resistance, so they're not supposed to have any power. But because there is some internal resistance, there's gonna be some power here. And R is gonna be equal to P cell over I square, which is equal to 0.58 over 0.7 square. So this will give you a number of 1.2 ohm. So this is the internal resistance. So now calculate the electromotive force of the cell. Electromotive force is going to be equal to current times internal resistance plus resistance of the variable resistor. So it's going to be 0.8 times 2, right? Because here 1.2 plus 0.8 is equal to 2. So this is equal to 1.5 volt. Right. So remember that electromotive force is supposed to be a constant. Problem 2. In 1997, a high-speed car of mass 1.1 times 10 to the power of 4 kilograms achieved the world's land speed record. The car accelerated uniformly in 2 stages as shown in the table. The car started from rest. Use the data to calculate the average acceleration of the car in stage 1. So you need to calculate the acceleration of the car first. So acceleration is equal to change in velocity over change in time. So in this problem, the change in velocity for phase 1 is gonna be equal to 44 minus 0, right? Because it's the car start from rest. And the time is gonna be equal to 4.0 minus 0, which is equal to 44 over 4 meter per second square. So the acceleration is gonna be equal to 11 meter per second square. Part B asks you to find the average net force required to accelerate the car in stage 2. So we know force is equal to mass times acceleration. And acceleration is equal to change in velocity over change in time. So acceleration for the car in stage 2 is going to be equal to the final velocity 280 minus initial velocity. So notice that the beginning of stage 2 is the end of stage 1. So the initial velocity for stage 2 is going to be equal to 44 I mean. And change in velocity is going to be equal to 12 minus 4. So this is equal to 236 over A, which gives you a number of 29.5 meter per second. So now you can calculate the net force. We know the mass is given by the problem. 1.1 times 10 to the power of 4 kilogram times acceleration. So this will give you a number of 3.2 times 10 to the power of 5 Newton. The total distance traveled by the car in 12 seconds. So we need to find the total distance. So as can be seen, acceleration in stage 1 is different from acceleration for the car in stage 2. So we need to calculate the distance for stage 1 and stage 2 separately. So the total distance is going to be equal to distance traveled in stage 1 plus distance traveled in stage 2. And distance traveled in stage 1 is equal to initial velocity square plus a half times acceleration times t1 square. Right. And because the car starts from rest, so initial velocity is equal to 0. So x sub 1 is going to be equal to a half times the average acceleration, so 11, times t square, so 4 square, and this is equal to 88 meter. So here should be 4.0, right? And now you can calculate x2. So let me erase. So how do we calculate distance traveled in stage 2? We know that final velocity square minus initial velocity square is equal to 2 times acceleration times distance. So in this case, the distance is x sub 2. And we know the final velocity and the initial velocity. So x sub 2 is going to be equal to final velocity minus initial velocity over 2 times acceleration. And this is equal to 280 square minus 44 square over 2 times 29.5. And this will give you a number of 1,296. So now you can calculate the distance. So this is equal to 1,384 meter, the total distance. And because 88 has 2 significant figure, and here has 4 significant figure, so we are only going to keep 2 significant figure for the final answer. So the total distance is going to be equal to 1,400 with a unit of meter. So this is the answer for this problem. The second part of this problem is about conservation of momentum. State the law of conservation of momentum. So conservation of momentum says momentum of a system is unchanged if there is no external force acting on it. Right? No external force. For any massive object, a space rocket is moving with a constant velocity. The engine of the space rocket are turned on and accelerate by burning fuel and injecting gases. Discuss how law of conservation of momentum relate to this situation. So you need to identify the system in this problem first. So the first system is the space rocket and the gases, the injecting gases. So let me write it here. So the system is the space rocket and injecting gases. And the momentum of the system is unchanged. Right? And because it says is moving at a constant velocity, so there's no external force. And because of conservation of momentum, the momentum of the rocket must be equal to the momentum. So I'm gonna write P to represent momentum of gases. Right. So this is why momentum of the system is conserved. Jane and Joe are two ice skaters initially at rest on a horizontal skating rink. They're facing each other, and Jane is holding a ball. Jane throws the ball to Joe, who catches. The speed at which Joe leaves Jane, measured relative to the ground, is 8.0 meters per second. The following data are available. Use the data to calculate speed v of Jane relative to the ground immediately after she throws the ball. So you can use conservation of momentum to solve the problem. So momentum, initial momentum is equal to final momentum, and the system is going to be Jane and the ball. So initially they're at rest, so initial momentum is going to be equal to v. Final momentum is equal to momentum of the ball plus momentum of Jane. Now you just need to plug in number to calculate velocity of Jane. So ball is equal to 1.3, velocity is equal to 8.0, mass of Jane is equal to 52, and then to calculate Jane. So velocity of Jane is gonna be equal to negative 0.20 meter per second. And because the problem asks us to find the speed, so you're gonna take the magnitude. So it's gonna be equal to positive 0.20 meter per second. Now you can find the speed of Joe relative to the ground. So I actually wrote it here. So to calculate Joe's speed, you also apply conservation of momentum. So initial momentum is equal to final momentum. But here's the problem. In this part here, this is not the correct working. Why? Because here is not correct. So let me just redo this problem here. So to find the speed of Joe, you need to apply conservation of momentum. Initial momentum is equal to final momentum. Initial momentum is equal to 0. But what is the final momentum? So from the problem, we know Joe catches the ball, right? So when Joe catches the ball, you can see Joe and the ball as a whole. So it is inelastic collision. Right? So it's equal to the mass of Jane plus mass of the ball times v ball. That's just the final velocity. Right? And then there's another thing, is the momentum of Jane. Right? And this makes sense, because this is Joe, this is Jane. After she catches the ball, they're gonna be in inelastic collision. So we know all of those quantity. So it's gonna be 75 plus 1.3, which is equal to 78.3 times their final velocity, plus masses of J, 52, plus velocity, 0.20. This is going to be equal to 0. So the velocity is going to be equal to negative 0.14 meter per second. But because we are asked to find the speed, so we need to take the absolute volume, which is equal to 0.14 meter per second. So 0.14 will be the answer for this problem. The first part of the question is about motion of a car. So a car is traveling along the straight horizontal road at its maximum speed of 56 meters per second. The power output required at the wall is 0.13 million watt. The driver moves the car in a horizontal circular path of radius 200 meters. Each of the 4 tires will not grip the road at frictional force between a tire and the road become less than 1,500 Newton. So let's take a look at the problem first. A car accelerates uniformly along the straight horizontal line from an initial speed of 12 meters per second to a final speed of 28 meters per second in a distance of 250 meters. The mass of the car is 1,200 kilograms. Determine the rate which the engine is supplying kinetic energy as it accelerates. So when the problem says determine the rate the engine where an object apply energy, is asking you to calculate the power, right? So let me do the problem here. So power is equal to energy over time. In this case, it's equal to kinetic energy over time, changing kinetic energy, which is equal to a half times mass times final velocity squared minus initial velocity squared over time. So the mass is 1,200, final velocity is 28, initial velocity is 12, and mass is 215. So this is going to be equal to a half times the mass is 1,200, final velocity squared 28 squared minus 12 squared over delta t, so change in time, is gonna be equal to the power. So how do we find time? Well, we know the distance traveled. So distance traveled is equal to 250 meters, and we know distance is equal to a half times final velocity plus initial velocity times time. And we know final velocity and initial velocity. So this is going to be equal to 28 plus 12 times time. So from this we know time is going to be equal to this 2 times 250 over 40. So this is going to be equal to 12.5. So now you can use T to calculate power. So plug in T, this is going to be 12.5. It's going to give you a number of 3,720 watt. And this is approximately equal to this, which is equal to 31 kilowatt. So this is how you solve for A. So this is going to be equal to 31 kilowatt. A car is traveling along a straight horizontal road at its maximum speed of 50 meters per second. The power output required at the wall is 0.13 million watt. Calculate the total resistivity force acting on the car when it is traveling at a constant speed of 56 meters per second. So let's do it. So we are asking to find force, and we know energy, and and y. We only know, we are asking to find force, and what do we know for this problem? We know the power and the speed. So how do we do this? Well, here's the thing. Energy over time is equal to power. Energy is equal to force times displacement over time, which is equal to force times velocity, and this is equal to power. So force is gonna be equal to power over velocity. So this is gonna be equal to 0.13. Meter 1 converted to watt times 10 to the 6th power over velocity 56. So this will give you a answer of 2,321 Newton, and you can also approximate this. So this is how you find the force. The second part of B is asking you to find the maximum theoretical acceleration when the car is at a speed of 28 meters per second. So how do we solve for this problem? Well, we can calculate the resistivity force by using this formula here, and then you can find the net force. So the resistivity force is gonna be equal to the answer we obtained here divided by 4. In which I'm not gonna work this out because we will use this, and the net force, or the accelerating force, is equal to 2,321 minus the resistive force. Right, so this is equal to the net force. And we know the net force, and we know the mass. So acceleration is gonna be equal to net force over mass. And the mass of the object is y. It is given by the problem. So the object has a mass of 1,200. So you can calculate acceleration. So it's gonna be equal to this quantity over 1,000. So 1 minus 104 is gonna be equal to 0.7475 divided by the mass, and this will give you an answer of 1.45 meter per second. So this is acceleration. Calculate the maximum speed of the car at which it can continue to move in a circular path. Assume the radius of the tire is same for each tire. So at the beginning of the problem, it tells us that the maximum speed is 56 meters per second for the car. The power is 0.13 million watt. And the radius for each car is going to be equal to 200 Newton. And the force for each tire must be less than 1,500 Newton. And because each car has 4 tires, so the total force will be less than 6,000 Newton. Right. And now you can solve the problem. So, force due to centripetal force is going to be equal to mass times velocity squared over radius, which is equal to 6,000 because it's gotta be less than 6,000. So we just assume it is equal to 6,000. Right. And we know mass. Mass is equal to 1,200, and radius is equal to 200. So we know that velocity is gonna be equal to radius times 6,000, which is 200 times 6,000, divided by the mass, which is 1,200, and this is equal to velocity squared. So you need to take the square root. So I'm gonna write it as to the power of a half. So this will give us the velocity, which is equal to 31.6 meters per second. While the car is traveling around the circle, the people in the car has the sensation that they are being thrown outward. Outline how Newton's first law account for this sensation. So you need to state Newton's first law first. So Newton's first law states that a object tends to continue its motion when there is no external force on this object. And then why do we feel like why people in the car feel like they're being thrown is because of inertia, right? So when circular motion here have velocity of v. So the body, the people in the car tend to continue their motion because of inertia, but the velocity is constantly changing direction. So this is why people feel like they're being thrown out of the car. Draw a circuit diagram. Also, this is about electricity. So let's look at the problem. A lemon can be used to make an electric cell by pushing a copper rod and zinc rod into the lemon. A student constructs a lemon and connect it in an electrical circuit with a variable resistor. The student measures the potential difference V across the lemon and current I in the lemon. So draw a circuit that will enable students to collect data for the graph. Cool. So you gotta have a cell, and because you are measuring current, you gotta have an ammeter, and then you have a variable resistor, and you need to measures the weight V electromotive force minus IR. R is internal resistance, so V will be what potential difference across lemon. So this will be the voltmeter. Show that the potential difference V across the lemon is given by this. So we know voltage is equal to current times resistance, sum of resistance, which is equal to current times resistance of the variable resistor plus the internal resistance of the cell. Right. So this tells us that V is gonna be equal to this plus this. So V in this case is equal to electromotive force. Right. So IR is gonna be equal to E minus IR. Right. So this will be the voltage across the lemon, and this is why the voltage is here, right? Because it measures the voltage of this electric component here. The graph shows how V varies with I. using the graph, estimate electromotive force of the lemon cell. So basically, let's see, you just need to draw a graph. Across the y-axis. So here's approximately 1.6. Right. So the electromotive force is approximately 1.6 volt. Using the graph, determine the internal resistance of the lemon cell, and then you need to calculate charge. Internal resistance. So internal resistance of the cell is going to be equal to the gradient of the graph, right? Because voltage over current give you the gradient. So the gradient should be in the range of 290 ohm to 310 ohm. So any number that is between this range should be fine. A lemon cell is used to supply energy to a digital clock that requires a current of 6.0 microampere. The clock runs for 16 hours. Calculate charge that flow through the clock in this time. So charge is equal to current times time. So 6 micrometer, convert that to 6 microampere. You need to convert that to ampere, and then convert 16 hours to second. So each hour has 16 minutes, and each minute has 60 seconds. So this will give you a number of 0.35 coulomb. So this is equal to the charge. A small ball of mass m is moving in a horizontal circle on the inside surface of a frictionless hemispherical ball. The normal reaction force n makes a angle theta to the horizontal. State the direction of the resultant force on the ball. Since the ball is in circular motion, the direction of the net force is gonna be the direction of the contributive force. So contributive force points to the center of the horizontal circle. So the direction of the resultant force will be point to the center of this horizontal circle. On the diagram, construct an arrow of the correct length to represent the weight of the ball. So we know weight is vertically downward. So gravity will also point downward, right? So this problem is very straightforward. And then we know normal force can be separated into two components. One is gravity and one is the contributive forces. So just make sure the lengths of the gravity they're similar. Right? Show that the magnitude of net force F on the ball is given by the following equation. So here we know this is gonna be the net force. Here is the gravity. Sorry, the arrow should be upward. So this direction is a net force, and this is gravity, and here we will have a upward force, right? So because the ball is moving on a horizontal, so the resultant force here is F net. So what you can do is this. We know here is theta, and we know tangent theta is equal to opposite over adjacent, which is equal to gravity So gravity is calculated by the formula of mass times gravitational acceleration over the adjacent set, which is net force. So net force is going to be equal to gravity over tangent theta. Right. So this this arrow here, I know it's pointing upward, but the magnitude gotta be equal to gravity. So the two forces balance off. So another method you can use to find the formula is this. So this is net force. This is theta. So net force is going to be equal to n cosine theta. And the upward force here is going to be equal to n sine theta, which is equal to gravity. Right. So from this formula here, we can say the normal force is equal to mg over sine theta. And then you can plot this equation in. So mg sine theta times cosine theta is going to be equal to mg tangent theta, because tangent theta is equal to sine theta over cosine theta. So cosine theta over sine theta is going to be equal to 1 over tangent theta, which is equal to mg over tangent theta. The radius of the ball is 8.0 meter and theta is 22 degrees. Determine the speed of the ball. So here we know how to calculate the net force. And we know net force also refers to the contributive force, which is calculated by the formula of mass times velocity squared over r. So mass cancels out, and from this we know that velocity is going to be equal to gr over tangent square, tangent theta, and then you need to take the square root here. So this is r. And from the picture here, we know r refers to the length here. It's pointing to the center. But how do we find r? Right. So the problem tells us the radius of the ball. So radius of the ball, let me do this. It's gonna be equal to r here. Right. So you can find this distance here, and we know the theta. So r is gonna be equal to the capital R times cosine theta, which is cosine 22 degree. So velocity is gonna be equal to gravitational acceleration a 9.81 times a cosine 22 degree over tangent theta, so tangent 22 degree, and this will give us a volume of 30.4 meter per second. So this is the answer for B. Outline whether this ball can move on a horizontal circular path of radius equal to the radius of the ball. So let's see if this is possible. So if it's moving on a circular path and this radius here is equal to radius of the ball, then it must be moving in this direction here. So this is gonna be the ball, right? But what happens is if the ball is moving on this circle here. So let me erase everything here. If it's moving on this circle here, the direction of the normal force will be pointing in this direction. So here is gonna be N. And then we have gravity. So no force will balance out gravity. So this is not possible. So this is not possible. And then you need to mention that because no force will balance out gravity. So r, the radius cannot be equal to radius of the ball. A second identical ball is placed at the bottom of the bowl, and the first ball is displaced so that its height from the horizontal is equal to 8.0 meter. The first ball is released and eventually strikes the second ball. The two balls remain in contact. Determine in m the maximum height reached by the two balls. Oh, determine in meter, I think. Sorry. So how do we solve this problem here? So we know the ball is initially at rest because it says it's released, and then it strikes a ball. It strikes the second ball here, and they stay in contact. And then they're gonna reach a maximum height. Let's say here, just a random point. So how do we solve this problem? Well, the first thing I think about is this. Since we know the initial velocity of the first ball is equal to 0 meter per second, and this is also equal to 0 meter per second. When they reach their maximum height, the final velocity is gonna be equal to 0 meter per second. And because they stay in contact for a while and they have an initial velocity, so we can use conservation of momentum to solve the problem. But in order to use conservation of momentum, you need to find the velocity of the first ball first. So just before they are in contact. So we know the height of the first ball is equal to 8.0 meter. Right. So because it's released from rest, so h is gonna be equal to a half times acceleration, which is gravity, by gravity. So little g here times t squared. And from this we know t is gonna be equal to the square root of 2h1 over g. And we want to find the final velocity before the two balls are in contact. So v sub 1f is going to be equal to acceleration times time, which is equal to g times the square root of 2h1 over g. So this is g is equal to square root of g squared times 2h1 over g. So this is going to be equal to 2h1 sorry, here cancels off 2h1g. Right. So now I can plug in a number. 2 times 2, 9.81 times 8, in which give you a number of 12.5 meter per second. Right. So now you can use conservation of momentum to solve the problem. So initial momentum must be equal to the final momentum, and the system will be the two ball. So initially the second ball is at rest, so we're going to have a momentum of 0. The first ball, because they're identical, so let's say their mass is represented by the letter m times initial velocity is equal to, after they strike each other, 2m times their velocity. So let's say this is v2i, because they're two balls. So m times 12.5 is going to be equal to m times v2i. And the m cancels off. So 12.5 is going to be equal to 2v sub 2i. So v2i is going to be equal to 6.25 meter per second. So this is when they stay in contact. So we have two balls. So let me draw it. So this is the first ball, and this is the second ball. Right. So this is their velocity. The maximum height reached by the two balls. So when they reach the maximum height, they gotta have a velocity of 0 meter, as I wrote it here. So how do we find the height? So we know that they have a final velocity of 0. And we know now their initial velocity is this. And we want to find their height, maximum height. So we know maximum height is gonna be equal to a half times what? A final velocity plus initial velocity times t, the time. But we don't know the time. So how do we find maximum velocity? So we can use the formula of final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. So in this case, acceleration is by Earth, so it's g. Final velocity is gonna be equal to 0. So h max is gonna be equal to vi squared over 2g. Here should actually be v2i, sorry. So this is gonna be equal to 6.25 squared over 2 times 9.81. So h max is gonna be equal to 2.0 meters.